These graphs contain a wealth of information about the machining process. You can see there's tons of data metrics that we can take a look at in graph form. I'm just going to use chip thickness and total force and give you some ideas how these graphs work for you and information that they can show. The graphs are interactive with the part and also with the NC program. So for that, we'll use the docked view of the NC program, and we'll put the part over here just where we can keep an eye on it. For starters, let's take a look at the first tool. Now I've got a couple of different graph lines going on here and some colors, so let me show them to you one at a time. This is the original NC program graphing that we can see for this first cutter, and the cut color that you see in the background ties to the color on the part to give you a clue of which machining operation or toolpath you're examining. Now looking at the graph activity, we see that it looks relatively constant, but you've got this red dashed line up here, which is the target chip thickness for this operation and this tool. So what the graph tells me here is that we're beneath that line by a significant amount, which tells me that the tool has not been programmed efficiently. There is one lonely spike right here, which kind of puts us in and around where that tool could perform, but the rest of it is performing to a substandard level, inefficient. We would like our optimization to fix that. So if we look at the optimized NC program, it looks quite a bit different. You'll notice there are no inefficiencies. All of the cutting engaged with material is occurring right at the ideal chip thickness for that tool. Now look at the cutting forces. They're still below the ideal cutting force of what this tool can withstand. So there are no problems with cutting force. Comparing the two, we're actually able to see with the dark green where the NC program was running, and with the bright green shows you what was raised in order to get the chip thickness where it needed to be. And you can also see the difference in force that was applied by increasing those feed rates in that area, none of which threatens the horizontal line for total force. Let's look at another tool. This particular tool demonstrates something else that force is unique about handling for you, and that's making corrections to the NC program when things are looking too aggressive. Anything above the red line, like all of these spikes in this area here, are excessive tool forces or excessive chip thickness, which caused these tool forces. Let's take a closer look. Again, the original NC program shows these force spikes, and you'll notice out on a real part in the shop floor there'll be chatter marks. This could be where a tool had trouble and an operator had to dial the machine back with his override, or maybe even the tool got damaged with broken teeth or snapped off. These are all things that can happen with too much tool force. In those areas, in order to keep the forces in check, what force optimization had to do was reduce the chip thickness below what the ideal amount should have been. But it had to do so in order to save the tool. This is the saving measure that VERICUT Force is unique in having to present the best tool life and give the tool spindle a break and not have any problems. So it keeps a constant running tool force in those areas, and you can actually hear that on the machine. So this actually is what improves your tool life. There's one more thing I want to show you about the graphs while we're here. VERICUT has a NC program review mode, which is linked to the graphs that allow you to go back and review any of these conditions that you are concerned about. So let's go back and look at the original NC program once again. And this time I will click in the graphs in order to have VERICUT put the material back to the state that it was in right at that time it was processing that motion. So here's the cut, and I can use my thumb roller here to go backwards and forwards in the graphs. So as the cut began, you can see it's right on the profile of the wall, a relatively light cut, and going forward, it gets into the corner. Still looks pretty good. You can see where the cursor is on the graphs here, the blue cursor. One more time. And then right here where it hits the wall at 90-degree angle, it opens up a cut around the face of the cutter, which is where all of the chip thickness was increased, and so were the cutting forces. And that's usually going to present itself as chatter marks in the corner. Some programs have a slow down feed rate for corners. This one obviously didn't. So what did Force do with that? That's where it had to reduce the feed rate. So it gives you automatic corner slowdown to make sure your corners come out nice and dimensionally correct. And then it will take off and go into the next corner and do the same thing again. So a very nice way of using VERICUT to be able to go in and analyze the tool motion and investigate problems to learn what's causing them.